Hello, everyone. Welcome to the third episode of Math and Beyond, and this podcast. Today, we will be talking with Bhavesh Rajpoot. About eclipsing binary star system. So basically, Bhavesh, he's a graduate student at the Heidelberg University, and he has been doing an internship at the Max Planck Institute of Astronomy. And yeah, so we will be talking about eclipsing binary star systems. I will now send him the invite, and I will see you soon. Hi, Bhavesh.
Hey, can you hear me?
Yes.
Okay. I'm so sorry, the Zoom started updating at the last moment.
Don't worry. There's no problem at all.
How have you been? How are you?
Yeah, I'm doing fine. There is nice sunshine today in the Netherlands, so it is very nice. Where are you?
I'm also good, and we also have kind of a sun out, but yeah, it was good yesterday. It was really good yesterday. Yeah.
Okay, great. Where are you located now?
So I'm at Heidelberg, University of Heidelberg. I'm studying at Heidelberg, doing my master's. Doing my thesis and my other projects at Max Planck.
So, okay. Yes, that's what I said. That's what I said before you were joining the call. I said that you are studying indeed your master, as you said, in physics and astronomy.
Yeah.
Right. Yes. Yeah. And at the Heidelberg University, and you're doing your internship at the Max Planck Institute for Astronomy. You are, specializing in radio astronomy.
Okay, not in radio. Now, I did some courses. I went to a summer school back in the bachelor's, but now more towards optical and mid-infrared. So going towards that domain. Yeah.
Okay. I understand. And I said, I introduced our topic of discussion for today, which is eclipsing a binary system of stars. But so first, if we want to jump into it, I would like to ask you, what is, before then an eclipsing binary system, what is a binary system? What do we mean by it?
Okay, so it's pretty simple, right? Like you can, like the name tells itself, you have two stars, and if two stars are revolving around each other, we get a binary system. And now and like binaries are the most common forms of systems or you can find in the universe. Like we have more than 57% or something, around more than 60% stars we found are in binary pairs. They are going to be gravitationally attached to a pair always, like majority of the times, like, and which also gives us the idea, which also gives us the hope that the sun should be, or should have been a binary before, way before, when it was being formed, when there was no solar system. But it looks like it got flung out from the cluster or something like that. But yeah, because majority of the stars form in nebulas, as you can see in one of the posters behind, stars forms in nebulas. So you have a lot of stars in a confined space, so they are going to be gravitationally attached to a lot of their pairs, or a lot of their brother sisters. Yeah, so you always get binaries. And now we get different kind of binaries. So you have sometimes a main star and a small star revolving around one star. And then you can get, for example, a triple star system. So you can have, for example, one system like this and another system completely like this. So this system should be at its foci of the bigger one, something like this. Then you can also have, for example, let's say two stars like this, rotating around a common barycenter. You can have quadruples like that. So as far as the mechanics are getting solved, as far as we don't get a chaotic system, we are good to go. So you can have triplets, you can have sextuples, even I guess the highest is 6 we have found in our observations, 6 stars together in a binary dance. But yeah. So
okay, and what is then more specifically, what is an eclipsing binary system?
So eclipsing comes from the techniques how we observe them. Now you observe the stars, you see if there are two stars very close by together, We call them visual binaries because it looks like they're very close together. And then let's say if you observe it for a few nights, and if you see two stars like moving around like a common, let's say, barycenter, or like they're shifting around together, not going or not changing the trajectory, but just wobbling around together, wobbling around through the nights, let's say 6 months, then you call them astrometric binaries. Then let's say if you observe that pair with a spectroscope, you call them spectroscopic binaries. And then let's say if you observe them photometrically, but if you see a constant or periodic dimming of of the brightness, then you call them eclipsing binaries. It's all about how we have developed the techniques to observe them. So for example, Sirius is a binary star system, but it's too bright that its fainter companion is almost outshone by the primary's brightness. So you cannot see it photometrically, for example. You cannot see it visually or on the images. But when we put a spectrograph, or we took spectroscopic observations of Sirius, we found out that its spectral lines are moving periodically around a common line, which gave away that it's a spectroscopic binary system. And eclipsing binaries are a special system. It's like they are also spectroscopic, but the speciality is that let's say if you have a primary here, and let's say you are the observer, so you will have a companion like this, and this will eclipse it at some point. And that's where you will have for example, constant light curve going like this, and when the stars come, you will get a dip, and then it will go back, then you will get a small dip, and this goes on and on and on. So this only comes when we are directly in the line of sight, for example. So we only get to see eclipses, and it doesn't matter that the eclipses should be directly in the front of it. You can have just a little bit above or a little bit below. You can still get an eclipse. But let's say if it's like this, something like this, where you can constantly see the secondary, then it's not an eclipsing binary. It still will be spectroscopic, but not an eclipsing. So it's just a special case that our line of sight just matches with their eclipses. That's it. That's the only thing it's special about eclipsing binary.
Okay. What do you mentioned? You mentioned throughout this explanation spectroscopy. Can you elaborate very quickly on what is spectroscopy and why is it used?
Okay, so we all have seen rainbows, right? So how light get dispersed from the rain droplets, and you see a spectrum, Vibgyor. So we do the similar thing in the lab. So you put let's say a slit, or diffraction slit, let's say, or your diffraction grating, or we basically divide the incoming light into its constituents. So we get spectra, we get the spectral lines of what the star is emitting, and you can get a ton of information from the spectra. You can get to know what kind of atoms or what kind of molecules currently in that star are, or let's say if the star is like this and there is some dust in front of it, and if we are seeing that light coming through that dust, then so the dust absorbs the light, but it's absorbs a specific portion of light, not the complete light, right? So if we get to know if there are dips at specific points in a spectra at specific wavelength, we get to know, okay, there should be this molecule or this dust grain of, let's say, polyachromatic hydrocarbon or something other, like maybe a simple hydrocarbon, let's say, should be there to make that dip in the spectra, to absorb that specific part of light at specific wavelength. So spectras are like atomic signature of anything in the universe. You take a spectra, you get to know its history. We take the spectra of sun to get to know what was the history of sun, what was the forming conditions of sun were, for example. So the very first stars only had hydrogen and helium, right? So you only see mainly hydrogen and helium in those spectra. But the later stars like that in that nebula, you see heavy metals also. So you see emission lines from heavy metal. You see emission lines absorption lines of heavy metals from the dust, let's say. So it gives a tons of information. And it's pretty crucial because you get to know the atomic budget of the system, right? You get to know what was the conditions, and then you can link, for example, let's say you observe this specific nebula in our Milky Way, and let's say if its chemical composition is not matching with Milky Way's, you will get to know that this was not the part of Milky Way from before, which means it was a part of from another galaxy which merged into Milky Way. So this opens the field of galactic archaeology also. So in spectras, we take the lines, emission lines, absorption lines, the lines where, let's say, specific atom is getting excited and radiating away that line, or a specific atom is absorbing that part of light, and we get an absorption line. It's like this. And when you, for example, if a source is moving far from us, that line get red shifted, the Doppler effect. If it's moving towards us, it gets blue shifted, again Doppler effect. So with the binaries, with the spectroscopic binaries, let's say if you are observing the lines like this, so this when the star would be like here, coming towards us, let's say, the lines will get blue shifted, and when it's going away from us, it will get red shifted. But this will be constant, right? It cannot change its orbit. So the amount of shift is going to be constant. It's like this. So let's say if you observe a H alpha line or hydrogen alpha line, so you will get a constant shift around the main hydrogen alpha wavelength. So let's say plus minus some, let's say plus minus 50 nanometers, plus minus 50 nanometers, let's say. So you get to know, okay, this should be its radius, let's say, for example. You can deduct things out of it. Yeah. So this is what spectroscopy or spectroscopic binaries mean, or how do we use that?
Okay. But why is it important? Why is it important to study these binary systems?
So, for example, let's say if you want to get the physical properties of how how stars formed, or how did they get here. So let's say if we are not in this solar system, we are from another solar system, let's say, and we are observing our sun. It's pretty difficult to know its details, right? Like you can only get the flux and the simple Stephen-Boltzmann law, flux F equals to sigma. F is flux is directly proportional to times to the power 4. So you can only get temperature, or you can only get size from the flux, but you don't get to know the, let's say, chemical constituents are until unless you do spectroscopy. You don't get to know where it came from. You don't get to know what was the forming conditions were of that specific stars. So there are tons of physical information we don't get to know just by observing flux. There are ways you can get that information, but the error bars are very high. It's pretty uncertain. So binaries gives us this opportunity of applying gravitational dynamics, right? You can apply simple orbit laws, Kepler laws. You apply that Kepler's law, you can get the mass of the system. You can get the mass of the primary and secondary star. You can get more precise temperatures according to that mass. You can get if you have the spectroscopic information, you can get its where does it sit in the CMD or color magnitude diagram or HR diagram, let's say, how old that star is. Is it an early type star, or is it a late type star? Sometimes we see a system where you have an early companion, like an early star at the center, but a white dwarf, which is a pretty late star, like almost the end stage of a main sequence star, revolving around it. So this is a kind of a unusual system, because this formed definitely later and this formed definitely afterwards. So you get to know the physics behind it, how the conditions were, why did not it blew it away, and all. So getting this opportunity of applying Kepler laws itself can get us a lot more details. How basically the masses, you cannot get masses from the fluxes. That's the only problem. You can get, but the uncertainty is pretty high. So if you want more precise answers, like what should be the mass of this system or mass of this specific star, you need binaries technically. So it's like this. And let's say if you have a black hole, let's say, you cannot get anything out of black hole, right? It doesn't emit. You can only see its gravitational effects, which means you can only see something revolving around it. That's the only thing. You can see lensing maybe, but the pretty easier would be to see what it's revolving around it. You apply basic laws. You apply the same law which you apply for a satellite moving in the orbit, V equals to under root of GM by R, and you get the mass, or you get the velocity, orbital velocity. And then from your orbital velocity, you can solve for the mass, and it's pretty simple. So you get to know the mass of the black hole itself. So this is how we apply these laws. You cannot get anything from a single star. That's the only problem.
Okay. Okay, well, then what do these binary system do they tell us about stellar evolution, for example? What grasp with regards to stellar evolution from observing these binary systems?
So they don't directly tell you about stellar evolution, but they fulfill the gaps in our in, let's say we are devising a hypothesis that if this star is, let's say, older than sun, but its environments are still younger than the sun, then why is that? So it fills up those gaps. There's a complete possibility that we might have observed wrong thing, or let's say if we observed or it was a false detection, let's say, then those gaps filled up. Or you get to know you need a validation, right? It's like that. You for example fit a model, but you need a validation that it's a good fit, let's say. So these other information gives us that validation. So for spectroscopic, you directly get how it's evolving. You for example, you plot its luminosity versus temperature, and you track where the system is, and this is what we call an HR diagram. And this is tell us how old a star is, let's say, or at what stage it's evolving. Is it already at a main sequence, or is it at a red supergiant phase? Is it already a white dwarf? That thing gives us the details of where it is or how it is evolving, let's say.
Okay, and what about instead on a, let's say, on a larger scale? What about the behavior of galaxies? What do these binary systems tell us about galaxies?
This is actually a really good question. Okay, so I think personally, I might not expect finding binaries in old galaxies, let's say.
Why?
Because they have already stopped star formation. So you don't have the conditions where you will get two stars forming nearby each other. So there is a possibility that galaxy might have binaries, but they might have already flunked out away. Some might have evolved. Let's say if we have a primary and we have a secondary, but this primary is older than this one and a huge one. So let's say this one goes a supernova, then the effect of this supernova might flung this out. It's a possibility. So
Okay.
so you will see binaries, but I will expect to see binaries, but a way loss. Their population is going to be way less. So I might expect a lot more binaries in a star forming galaxies, and specifically at where nebulas can form. So specifically at the arms of those galaxies. So let's say if I find a binary star system in a galactic halo where the older stars form, then I would be surprised. I would be like, okay, this is an interesting system. I want to know its history. How did it get here? Was there a formation event happening in the galactic halo before and now it's not? Or maybe did it get flung out from the arm? Or maybe it's a remnant of a merger? So you get to know like what happened with it. At least I would like to know that. Yeah. So
Okay.
it's like more minuscule details it gives about galaxies. It might not tell us more about galactic evolution, or it might not itself affect the galactic evolution, but yeah, it can affect if if I can expect having more exoplanetary systems forming in that system, more in detail information, let's say more precise information, I would say. Yeah.
Okay. And I think you mentioned before, why do we have, that we see from Earth, we see the light, the brightness of this binary system to become faint sometimes. Why does that happen? Because I think about the sun or whatever other star, I wouldn't expect to see changes in the brightness of the sun. Why do these changes in brightness occur?
Okay, so talking from the perspective of binaries, let's say eclipsing binaries. So it's more about change in the relative brightness. So let's say if you have two stars, they're like very, very far away, right? Like, so their distance is like almost negligible for us. Like they're like too close for us to differentiate if they're too far away, right? Okay. So like on my CCD, on my photographic, let's say on my photographic CCD, I would see it as a one object, but with a combined brightness of the two. So I would get a summed up flux from the two, right? But let's say if if my secondary is blocking the first one. So there is a part where and the primary is more brighter than the secondary. Let's assume that. Then the dimmer star is actually blocking a good amount of, or large area of the brighter part, which means you will get some reduction in the light. Like it won't get dim. It's like just blocking that part. Like you will see more of the dimmer one, which you would seeing like, let's say at this phase, but here this thing is like now blocking the brighter part. So the dominant source of brightness of that combined system is now behind that secondary one, right? So you get the dip in the relative brightness, not the actual brightness. So they never get dim by their own. It's just the way, we are seeing them. So let's say if for us there is eclipsing binary, but let's say we are in the Star Wars era and you are in some other solar system, it's completely possible that it might not be a binary for you at all, eclipsing binary for you at all, because the angle of line of sight would change, right? It would completely change for you. Like for me, if it like this, for you it would be like this. If for you it would be like this, like revolving like this instead of this. It's like this. So it's completely relative to us. So nothing happens, astrophysically happens there. It's just
okay. So I would say these changes in brightness, they do occur because of our relative location compared to them. It is not an absolute fact of this object. It really depends upon the point you are observing these objects from, right? Okay.
Which is actually a very good thing, because let's say if there is dimming happening, then it's like one more challenge for us to solve. Like, why now dimming is happening? Now I cannot account for the accurate mass or the accurate temperature. We don't want anything to affect that brightness intrinsically at all. If there is a blocking source, let's say if there is a dust cloud coming up like in front of it, we are still taking relative brightness, so it will affect both of them, not a single one of them. But of course, we live in non-ideal world, so we do get dimming. There are sometimes, let's say, for example, we have sunspots, so we have star spots also. So sometimes what happens that if the primary is rotating and the sunspots come ahead, you again get a dip, even though if the secondary is not what do you say, blocking the first one. The dip will be pretty small, but you will definitely get the dip. And we have researchers just like looking for that dip, how big, and they can get how big the sunspot was, let's say, or how big with respect to the whole star, how big it was, let's say. And sometimes we are getting in that era where we are getting more precise observations. For example, so let's say if there is a stellar activity happening, if it's a huge star, if it's a blue supergiant, let's say, if there's some stellar activity happening, if let's say I have a spot, a dark spot there, there are effects where I can get, for example, let's say if I get a bright flash, let's say a CME from there, or let's say a solar flare from that specific spot, a very huge solar flare to get detected on a CCD, then I can get to know what kind of stellar activity is also happening there. So sometimes this specific technique again is used by heliophysicists, but for completely different reason, not for getting the mass, but for getting what is exactly happening. And they can only do this for very, very huge, very, very bright stars. Because for the smaller ones, the effect would be so small that for us, it would be below our noise range, So we need with good signal to noise ratio detections. So sometimes you do detect flares, very huge, very strong flares, of course. So strong that let's say a flare of that scale happens in the solar system, that the solar system won't survive it at all. But we do get to see that, and we do get to, and that's why these work as exotic laboratories for us, right? You cannot you cannot do that in your laboratory on the earth. It's just simply impossible. You still need to test the extremes of physics. You get cataclysmic variables. This is what we call cataclysmic variables. So let's say if you have two binaries and if they're closer together, have you heard about Roche lobes? Sometime during...
No, I don't think so. No.
So, okay. You must have seen that curved space-time diagram, right?
No.
pretty basic diagram, right? Like we have seen from the Einsteins. So it's like so every object has some gravitational potential well around it, right? So you can have it like a specific boundary where like beyond that boundary you won't feel the effect of that object that much, but after that boundary you will get like pulled towards it. It's like something like this, let's say. So we call this Roche lobes, and you can derive it from, let's say, gravitation by solving the equation of gravitational potential, let's say, by using Hamiltonian. So if you do that, you get some Roche lobe, and it looks like teardrop shaped, let's say, for example, for 2 stars. So it's like something like teardrop shape for both of them. And the central, yeah, and the central point will give you like the point where the force from this star and this star is equal. It's like this. So it's like the Lagrange points where, for example, JWST is right now at the second point, and Lagrange 1 point where the solar observatories are right now. So it's like those Lagrange points we have around Earth. And that is only that comes by equating the gravitational force of Earth with respect to Sun. That's it. So you get those points where you have the same force applying on your body, no change at all. So you put something there, it's going to stay there in an ideal world. Let's say if there is no external force, it's going to stay there forever. It's like this. So sometimes if you have very massive objects, and sometimes if they're too close by, like in that cluster, if they're too close by, their Roche lobes kind of connect together. So Roche lobes, for example, of two isolated objects would be circular, let's say, on a 2D plane. But if they're closer, then they will get a teardrop from both the ends, like something like that. So now if you have, let's say a star, like 2 stars, one is older, one is younger, let's say, but the older one of course evolves sometime. At some point its hydrogen is going to get depleted, right? It will start burning helium, it will get expanded. But now when it expands, it doesn't have enough space to expand, so it fills its all the Roche lobes, and then the extra matter will start falling on the secondary from that Roche lobe connection. It won't go out like this, it will go to that connection. So if you have like this, you will see matter flowing or falling on the second one. And then that star starts getting accumulating matter more and more and more and more. And then at some point its gravitational force will overcome the radiational force, or like say radiation pressure, and it will go, let's say, supernova, and you will get a white dwarf by the end, let's say.
Okay.
This is what we call type 1 supernovas. We know how it forms, and that's why they're like standard candles. So you get this like mass transfer happening between two, and we call them as cataclysmic variables. Sometimes, let's say if the 2 stars of the same age, they evolve together and they both get connected. So you see 2 teardropped stars moving like this in the sky. They're pretty cool. They're pretty cool. The physics happening at the end of it. It's really cool. Yeah.
But
yeah, too tricky to solve, but yeah, really cool.
I can't believe it. Unfortunately, I've never had the chance to see one. Okay, but you mentioned before that we can learn about the physical properties of this system and about the star composing this system. But how do we know? How do we know about that? How do we learn about these physical properties? I found, while checking for this topic, while reading a bit about this topic, I read that we could use the light curves of this system. So what is that? Why do we use that, and how we can infer physical properties through that?
Do you mind if I show you that on my screen? Like I
yes.
think that would be pretty much.
You can share. Yeah, you share your screen. Absolutely.
Yeah. Can you see my screen?
Yes.
Cool. So which I have. Okay. So this is what the light curves, for example, or sorry, radial velocity curves look like, and this is what a light curves look like. So yeah, which do I have a better? Yeah, this would be fine, I guess. Can I make this large? Okay, perfect. Okay, So let's say if you, for example, this is what I was talking, you get the summed up flux, and you get the dimmer in front of the brighter, you get main eclipse, then then that dimmer star will go at the back of the primer or brighter star, you get a smaller eclipse, and this happens. So this is what we call a light curve. Light when it's curving. Simple as that. Yeah. And like, and this one is pretty cool. You see a star, you see a combined star in the sky, like going like this. Then the eclipse happens, then it gets dimmer, and the eclipse gets over, and then you see it again bright. So you can see those kind of effects in the star trails, let's say. Yeah. So this is how we got to know, like, there are like there is something something is going on there. But yeah, and you can have, like, for example, different kind of configurations. Yeah. And you need to solve for different kind of physical effects happening to get the exact, let's say, light curve. So you might start with a very simple assumption, then you add a part of physics, then you again add a part of physics until it gets, like, better.
Okay, so we have the dips in those graphs. They do represent the moment when the brightness gets fainter because one of the two stars is eclipsing the other. Okay.
Exactly. Yeah. And this is a pretty cool table from one of the papers, like, which I referred a lot. So this is like, so these are all the parameters we aim to find about the stars, let's say, or the systems. And here, like, how we observe it tells us, like, how many parameters we can get out. So for example, from astrometric binary, let's say, alone, we can only get these 5 parameters, or like, 6, 7 parameters out of this whole list. With let's say, with radial velocities, we can get a lot of it, but not the size parameters. So for example, we might get to know what its velocity is, but we might not be able to get to know what the size of the actual star is. And size kind of matters a lot, right? Because if you see in this diagram here, let's say, so, like, for example, let's say if this is a star, you get a pinpoint object, but ideally like, it's for example, if you draw a radial profile of the star, if you cross a line across it and measure the brightness, it should get cut at some point. That should define the radius. But the problem is our night skies also have a brightness, so you never see that. You see a Gaussian, so you never actually get to know what the actual size of the star is just from its photograph. Never. So this is again a very crucial information we can get from the binaries, which we cannot get from a single star. But yeah, so, and if you see, this is the, like, column of eclipsing binaries with radial velocity observations, let's say, and you can get almost everything out of this table, almost everything. So a huge, I would say, sorry, not huge, but a very highly important tool to get all the physics out of it. And then we can get to know, like, what's actually happening there. There is a complete possibility that we might find a system or a star which would have, like, which would weigh lighter, but its radius is huge. So we might expect it to have, like, huge convective cells. It's not like a sun, like something like a brown dwarf, something like that. So this, like, clears a lot of questions for the astronomers. And which I will go. Okay.
What are one of the, let's say, the main physical? You showed some parameters we can infer for binaries. What are some of the main physical properties that we can infer through the study of light curves?
So from light curves, we aim to study, like, something like this, like, cluster age. Let's say, like, if we get to see 2 stars, we can identify if they were a part of the cluster or not by their spectroscopic redshift. Then we get to know about their mass, their radius, their surface gravity, their effective temperatures, their luminosities, their systematic velocities. These all are important because you then apply the actual physics here. Let's say if you need to simulate a specific condition for your observations, let's say, or for your thesis, or sorry, for your hypothesis, So you can put this information in a simulation that it should work like this. You should have this. You should have this starting parameters. And if something deviates from this, then you're going wrong. Then the simulation is going wrong. Then model needs to be changed. It's like that. So all of this basic information gives me the idea that yeah, the physics is happening right. And if it's not happening right from us, then our model needs to get changed. Yeah, simple as that. But this is how, this is why this mass, radius, and effective gravity, effective temperature, these are the main parameters we aim to study, let's say. And your doubt with the light curves. So for example, if you observe a primary, if you observe the secondary dip, now in the secondary, the secondary star is at the behind of the primary, right? So you only get flux from the primary star. So this distance, let's say this amount of distance is its actual brightness of the primary, relative brightness, but the actual relative brightness of the primary. And by this, like this dip shows when the dimmer star blocks the brighter star. So now by its width, let's say, for how long the primary was, like, in front of it, you get to know how big the star is, how big the secondary star is. So so by the area of circle, so by using pi r square, how much area it was blocking on the primary star, for example. And again, and this width, for example, when the secondary is behind the primary, so you get to know for how long it was behind, right? So if a star is bigger, it needs to cover a bigger arc, let's say. So you get to know the size of the primary. So this is how you deduce a light curve, for example. And you can have bunch of information, a bunch of equations. For example, there's a set of some equations you can do. And let's say if my system has eccentricity, it's not a circular system, it's in an elliptical orbit. So the distance between the duration between the primary and secondary tells me its eccentricity again, which is again we cannot find out by on our own if we don't have this system, for example. And so this is how it gives us the information. And this is what I was telling you. So for example, if the secondary star is directly in the front, so if it's directly at the head horn, so you will get this light blue, like this aqua colored curve, which is the complete for example eclipse. And let's say if this star starts going upwards, like for example from here to here, let's say, then its shape starts getting changed, something like this. So from the shape also you find out what is the inclination of the secondary is from with the respect of primary. And getting inclination is very important, because from spectroscopic binaries you only get relative masses, for example. So you plug in the inclination, you get the actual masses. So that's why you cannot only use spectroscopic or only use eclipsing. You need both of them to get all the physical features out. And if you see here, this is a little bit curved, right? So it should be straight because it was completely behind. Let's say it should be straight, but this is a little bit curved. And this tells us about the limb darkening effect of the stars. So how big the star is, and the limb darkening gets affected by its surface gravity, how strong the gravity is on the surface of the star. If it's very stronger, the limb darkening is going to stronger. If it's not that stronger, it's going to be brighter. So you start getting more physical details of the stars. So it's like this. Yeah. I hope that's yeah, and not too much details or technicalities.
No, it is very interesting. I've never dived into this topic. I believe it is fascinating how much details we can actually grasp from these objects.
Yeah.
But how do so basically we said you mentioned before radio astronomy. How do radio astronomers how do astronomers use radio telescopes to study these systems?
Yeah. So again, this is a pretty good question. So I think, in my opinion, at least, we cannot use them that much because the primary thing which is happening is like dimming of the brightness. So like radio telescopes won't pick that much information. Like there's this only one case which I can think of is, let's say, if you have two pulsars in a binary orbit, and the jets are something like in our direction, let's say in our line of sight, that's a pulsar. So after every rotation, you of course get to see the change in the frequencies, let's say, of the, because at the jets of the pulsar we get synchrotron radiation which emits in the radio regime, which radio telescopes pick, for example. So we if that motion is happening, we get to see the change in frequencies of that emission, let's say, for example, with respect to us, of that star. And then again, if there's a case where two of the jets are merging at some point because of that orbit inclination in that particular fashion, then you get to see that boost in the actually that would be a pretty good source for a fast radio burst now I think of, but I don't know. But yeah, so you get two jets together would give us a very huge boost in our detection, right? So it's like this. So I think only in the case of pulsars or in the binary pulsars, we would be able to use radio telescopes or radio frequencies to detect them, let's say. Yeah, but there could be cases, but unfortunately I cannot think of it right now, and I've never heard of one. Yeah.
Okay. And how do okay, well, with regards to radio telescopes, but recently we have had a major discovery of gravitational waves. I mean, recently, some time ago, but relatively recent, we had the first detection of gravitational wave. How do gravitational wave detection technique can be used for studying in these systems as binary black holes, as you mentioned before? How can they be used? And are they turn out to be helpful, more helpful, and why? If that was the case.
This is again a brilliant question. Okay. So there are two cases which we need to understand, in my opinion. Again, first is how we are using eclipsing binaries. We primarily use eclipsing binaries for, or let's say binary stars, from the respect or from the point of view of the technique we have used. Either we have used spectroscopy, either we have used photometry, like this. Black holes are again exotic objects, highly compact objects. So
what do you mean by highly compact? Highly compact?
Okay, so let's say if you if we have our sun, and if we, without losing any matter, if we compress it for the size of, let's say, Greenland, let's say, of the size of Greenland, then it's a compact object. It's like too much of mass in a small volume. Highly compact. So it would have a higher gravity. Exactly.
Okay.
So, but that's the thing with the black holes, right? You don't see anything coming out of them, right? You can only see its gravitational effects. So either they are curving the space-time in such a way that the light behind that black hole system is getting lensed in a periodic fashion. So you get to see, for example, those kind of systems again. For example, we have cases where we see eclipsing binaries, but with a white dwarf, let's say, and that white dwarf causes gravitational lensing in the front of that primary. So that also happens. And sometimes if the inclination is high, it goes behind like this, but there's a curve like this. So you don't see dip in that case. You see a reverse dip in that case of compact binaries with compact objects, let's say with white dwarfs, or let's say with neutron star, which has very high gravitational field, which can bend light coming towards its way, let's say, for example. Or you can, so there are multiple cases you can use. But let's say if you have two black holes, it's almost impossible because they don't emit anything. If they have accretion disk, they might, but it's going to be a very, very messy light curve. You don't know how something is getting eclipsed or not. You might see a wobbly pattern kind of thing. It's almost impossible. So gravitational waves open this new regime or new era of studying those binary objects where we cannot detect light coming from them. So we want to know, for example, what kind of mass that black hole has. So there's this cool diagram from LIGO Commission is that we for example, they know how the smaller less stellar mass black holes come after, for example, like supernovas and everything. And they kind of also know how the huge supermassive black holes come by merging of a lot of black holes together. You get a supermassive one. But there was this one detection where we when we measured the mass of the black hole, it was an intermediate mass black hole, and we really don't know how that can happen. Like that kind of black hole should only happen if we have if the individual black holes have a certain mass, and those were already outside the limit of stellar mass black holes, almost like at the edge of the limit of the stellar mass black holes. So it made us think about it, like what would have happened that we got first of those two black holes and then it merged to get an intermediate mass black hole. So which basically hints about that there should have been multiple collisions before, or multiple merging before, sorry, and then it get merged to get a intermediate mass black hole. Because when that happened, so let's say if you have a 10 solar mass black hole and if you have a 25 solar mass black hole, if it merge, you don't get a 35 solar mass black hole. It's a little bit less because it also loses some kind of some amount of mass through energy when when it's getting merged. If you've seen that blip kind of signal, this is where it happens. When the inspiral happens, gravity is again their potential is so high that it start wrapping the space time around it, and the rotation, the coordinate systems get completely changed. We need coordinate systems which get dragged by those kind of systems. We call them Kerr. I think that is Kerr, I guess, maybe Kerr coordinate system, something like this. I don't remember, or Squash. I don't remember, but yeah. But yeah, you need coordinate systems which can get dragged by that frame, because each black hole would have with a different frame. Let's say you can assume like that, and so a huge amount of physics happen, completely extreme. So those, and again, that's the whole point, right? We, for example, if Einstein gave general relativity, we need to test it out. As an observer, as a observational astrophysicist, it's my responsibility to either prove it again or either disprove it again. Like I live by that. I live by that every day. So so LIGO gives me that opportunity. Now I can finally do this. You need extremes to test a theory, right? So you get those extremes there. We were not able to get that before from the in the visible spectrum, but now in the gravitational wave spectrum, we can get that. We can get those wave signals. We can find out how they started inspiraling, how much time did they took for getting in spiral, which means how much energy did they lose during that in spiral through gravitational waves. And when the spiral happened, how high the signal was, and again how much energy get radiated away from that blip or from that in spiral, and what was left behind. And this is with the black holes. And there was this really cool case when we saw two neutron stars merging. And this was a pretty rare case because we have there is this cool app on Android and iOS. We call it Chirps. So it chirps, something like this. And it tells you we found so it's basically updates from LIGO, from Hanford and other system. So you get updates like, okay, we found another system, we found another system, we found another system. So there is a huge list of two binary black holes, but there is a very rare conditions where you get two binary neutron stars merging, because there you see again a huge a different level of details, because now you have two compact objects, it inspires together, it radiates away energy both in the gravitational regime and in the electromagnetic regime. After the inspiral, it becomes a neutron star, let's say, if its conditions apply. if the degeneracy is not that much high, it becomes a neutron star again. And then after that, you see two kind of jets going from in the orthogonal direction of that merging plane. And that jets is highly important because, for example, those jets proved where gold came from. Gold cannot form from normal conditions. You need cataclysmic events to form gold, titanium, platinum. So, and which again gives us this thing like how the hell gold ended up in at Earth? Was it a meteorite which has a lot of gold and like it got stuck with the solar system? Was there already a two neutron star merging event happened before the formation of the sun itself? Like we don't know that. And it's kind of mysterious. Like how did the really heavy metals came here? Like it's like it boggles my mind actually. But yeah, the gold, for example, gold, silver, they can only form, for example, at the accretion disk of black holes or at the two neutron stars merging together. There's a really cool periodic table. We call this uh, periodic table of nucleosynthesis, and it tells us where each of the element came from in the universe. Either it came from Big Bang, either it came from normal hydrogen fusion in the sun, let's say in like sun-like stars, or did it came from supernovas? Did it came from white dwarfs merging? Did it came from black holes or black hole accretion disk? Did it came from two neutron stars merging together? So it gives you all those details, and you will get surprised by a lot of elements which are just simply impossible. Like intuitively, it's kind of impossible to get them here in our system. We like for the hundreds of light years, we don't have a two neutron stars together, or we don't even have a cluster. Like our stellar neighborhood is pretty sparse. Stars are very far away, like in our stellar neighborhood at least. So it's and the recent study, we have this paper from the last, I guess, from the January 2022, yeah, something like that Milky Way is one of the oldest galaxies in the universe. It formed I guess some 10 billion years ago, something like this. Like it started forming very early. So it's not like it's a new galaxy, so you can have a lot of heavy metals already formed from the events before. So it's a relatively old galaxy. It's a very old galaxy. So it must have had mergers, a lot of mergers to bring that kind of elements into our system, and specifically at this place where the sun is located. So again,
we were just lucky.
Yeah, the more we find out about like these things, the more questions arise. The more it doesn't make sense. Why are we observing this? Why it is like this for our case? Really,
it's pure coincidence.
Yeah, trust me. And when we show that in our, for example, decadal survey or like any surveys, like we call it like this is the funding opportunity. This is where we need funds. Save that space. Yeah.
So you believe that at least with regards to black holes, you think that gravitational wave astronomy can be fundamental in say trying to unravel these exotic objects indeed?
Exactly. Like there's a ton of information we don't know about the black holes, like literally, like nothing can get out of it. So all of the usual techniques fail, right? We cannot see light coming out of it. We can only see its gravitational effects. Before, we were trying to estimate the black hole masses from the effect of gravitational lensing, by how much amount a light curves around that object. That is going to be a direct function of its gravitational potential. So we were only able to do that from those techniques, but this opens a whole new regime. And this gives us pure information, right? Because, for example, if a supernova happens, now this supernova would happen, let's say, in the galactic center. There is a huge amount of interstellar dust in between the galactic center and us. So a lot of information get lost. So we at Max Planck, we have a team, we call it a Gaia team, and the Gaia team, and there's another team in the PSF department who work on dust, on the on the galactic dust we have in the interstellar dust we have. If they are able to map that dust, then we can exactly remove that portion from the observation, so we get the actual thing which is happening behind. But we don't know what's in between. So the team is trying to create dust maps for finding what kind of densities, what kind of extinction we get in between the observations from the perspective of Earth, let's say. And then for example, if I observe an event, I will need that dust map to remove the effect of the dust in between, to see the pure physics happening at that event, not something happening in between. So it but now this only happens with electromagnetic waves, they get absorbed, they get radiated again.
Mhm.
You don't have these things for example, these gravitational waves. You don't have those things. So it can just directly pass through it. It's the stretching and contraction of space-time itself. So there's nothing which can affect it or interrupt it or disrupt it, anything. Like we get the pure signal. So those pure signal means lesser uncertainties, which means more precise data, which means more precise physical deductions or tests or theories. Yeah. So that's why it's
And we hope to to hear some positive news on the discovery of these objects. But yeah, so what can you tell us a little bit about the last let's say more recent discoveries now with regards to eclipsing binary systems? What do we know? How the, let's say, have questions arisen that we are not pretty much able to reply at the moment?
Okay, so I think the first analysis began pretty early. So we have really good models which can get the physical properties like mass, radius, temperature of the stars. So now we are more interested what's happening on them. So for example, as I said, I don't, for example, if I'm observing an eclipsing binary, I don't want something happening intrinsically to that star, because that would be a different physics I have to account for. But now the astronomers who are working in this field are focusing on that part, because you do have intrinsic effects happening on the star which affects its brightness. So we got, for example, one of them is stellar pulsations. So the star pulsates at a specific stage of its life, it starts pulsating, and that pulsation can again reveal a lot of things or a lot of details about its internal structure. So those kind of pulsations are are important to test these the theories of stellar astrophysics, or stellar hydrodynamics, let's say. So so those astronomers are trying to observe those pulsations and deduce it that is happening. So that is one of the things which we are still doing, and we need more precise data for that, because let's say if you have small pulsations happening, then again it will go beyond the noise floor, and then you won't get good detections. So for example, tests revealed a lot of good candidates. I've worked with two types of data, one taken from the ground, one from test, and the difference was huge. I mean, literally huge.
Why?
Because it's more precise. You don't get what do you say, atmospheric aberrations, or you don't get turbulence from the sky. So test is in the space, you get so you are diffraction limited, not seeing limited, so you get more precise observations. That's the whole reason. So because again, here the star, the because of atmosphere, the star gets wobbled. So if there are pulsations happening, we might not be able to see it because of our atmosphere itself. So tests gave us this highly precise data set, and you could see there is something happening, there is something getting repeated, for example, of that signal. So for example, if you take a Fourier transform of that signal, you get frequencies out, right? From the time you convert to the frequency domain. So if you get one frequency, it's a normal eclipsing binary, how the light is getting dim periodically. But if you get two frequencies, then it's going to be interesting, because something is happening which is causing that frequency to come in the picture. And if you get, let's say, 8 frequencies, then yeah, it's a nightmare for us because there is a tons of things happening and we don't know what's happening. Yeah, but this is what happens. So I think that is the last when I worked is what we are trying to figure out those stellar pulsations and how robust we can make these models, because eventually we are going to send more highly specialized satellites or highly specialized telescopes in the sky. So we are going to get more precise data set, but it will be wasted if we don't have robust models. So there's a team, for example, in the in US. I forgot the name. The team is led by Andrej Persa, and he is, for example, leading this whole group for making good, robust models, which he calls physics of eclipsing binaries, named as Phoebe. So
Okay.
they are trying to create more robust models, because you need a lot of things. I worked with them, and I thought it's going to be a simple problem to solve by gravitational dynamics. It wasn't. It took me a year to just understand what the hell is happening there. But yeah, you need stellar grids, you need photometric simulations to create the same effect which is happening on the star, so that we can fit our model. Like sometimes the curve just won't fit, like the model was lacking. We get so irritated by it, like it's just not fitting. Yeah, just not fitting. So there's a huge work going on, because solving an inverse problem is always difficult, right? Because, for example, in the forward problem, you create an effect, you get an output. But the problem is, with the inverse problem, you can get the same effect from same output from the 10 effects. You don't know which effect is the right one happening with our case. So you need multiple effects to confirm with all together, doing a cross validation to see which is actually happening. So solving it it's pretty challenging. So in their model, I guess they have for one star, they have something around 16 to 18 parameters. And so you have a binary, so it's like double, so it's like 32. Yeah, something like that. So I think 32 to 36 overall parameters. So you have a 36 dimensional space which you need to solve. So I've kept I remember I had a old Windows laptop back then, running on i5 and 8 GB RAM. And when I used to do Monte Carlo solution of my fitting, like it gets so hot. I had to keep it in front of air conditioner so that please don't get burned, please. I did not have access to GPUs and everything, and I was bad at coding, so I could not do SSH on everything. So I was
Yeah,
like,
that you,
please.
you had to put it in the refrigerator, not to let it burn.
I for a moment, like it got so hot, I had to do that. Then I got get that. Oh my god! Like no, please, moisture would go inside it. Like no, I had to take it out. I'm literally like i5, like so literally without GPUs, it was a nightmare. I had to create a Telegram bot. So I used to put it before going to sleep. It will keep running, and then on Telegram I used to get updates. Okay, this is happening. This is happening. Okay, nice, very nice, very nice. I'll go back to sleep. Okay. So yeah, I had pretty fun days back then. But it was nice. But the parameter space is huge. You need GPUs, you need robust models to solve them. We don't solve all the still we cannot solve all the systems. It's again a nightmare. So this is what's happening right now. We are trying to making our models perfect, and then eventually we will try to put those models. We can put those models in the in the cosmological simulations, like the illustrious simulations, which simulates how the whole galaxies and cosmic filaments form. So if we put those kind of model in that, we can go into more resolved details. You know, if what's happening, if we have binaries happening inside the galactic galaxies, so for something like this, and there's a possibility that might affect galactic evolution. We don't know. That's the thing. And again, funding opportunity. So yeah, this is
Okay.
what's happening. Yeah.
It is very interesting, however. But yeah, I would like to ask you a couple of the last couple of questions, but not to spend much time because it is more, let's say, much more personal opinion, let's say, than anything factual. The first thing I want to ask you is sometimes when I read books about the universe, our cosmological theories, the history of the universe, I see how the discovery of our universe, and all the objects that we have found so far within it has always been bound to light. Okay, so light is literally the only, it literally is the only, I would say, tool that we can use to find about this object, to discover about this object. Light as visible light, but the light as, I would say, including all the wavelength of the electromagnetic spectrum. And the thing is that I sometimes I would say, I get thoughtful, I get, I would say, concerned about this. So the speed of light is finite. So we have an intrinsic and fundamentally limiting factor in light. And we know for sure, like this is a fact, that we know for sure the universe is actually bigger than what we are able to see, what we have been able to see in the observable universe. So what I sometimes say to myself is, but there must be something else through which we can see and study the universe. We cannot be only constrained to light. And then, of course, this is just, how do you say, pure, not even speculation. This is just a wishful thinking, because I clearly do not have anything else to propose. But I sometimes happen to say this: there must be something else other than light, because otherwise we will always be bound to see this, and we will always be bound to, let's say, only improving the method through which we can study light in all its shape. But there must be something else such that we can step up in the observation of the universe, of our surrounding. What do you think about this?
You're completely right. And this was the whole thought process by which ESA got funding to create a space-based LIGO system. So I've just heard about, I heard about in the news, like there should be gravitational waves, like very, 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 very dim gravitational waves coming when the universe, for example, when the Big Bang happened. So, so Big Bang, for example, it's kind of, I think it's kind of a misnomer, because for a long time I used to think like something exploded and everything, but no, it just came, there was no up, there was no down, there was no light. You must have seen what do you say, Dr. Green, I guess, on Twitter, talk about it, and the reels, there was nothing, the time itself started, we start our time from the Big Bang itself. So there was nothing, something just came from the quantum fluctuations and started to happen. But those things must have created events where they should have radiated away gravitational energy. And this is what we bound to test. For example, from the space-based LIGO systems, let's say. So that might change a lot of things, a lot of understanding. Because as you said, so Big Bang happened, everything came in the picture, quarks, photons, gluons, everything, all the standard particle, matter, antimatter, everything came, and everything was homogeneous. The whole universe was homogeneous. So it was just like a bright blob. That's it. Bright blob, completely homogeneous.
Yeah, like a sort of a soup.
Exactly. We called it cosmic primordial soup. Yeah, astronomers love fancy word, So cosmic primordial soup. Yeah, so completely homogeneous. But good thing is the photons come from that part. So that is the first 3 minutes are really important to know what happened and why it happened in such a way that we are here. For example, the whole I forgot what the hypothesis. There's this famous philosopher which said there should be specific conditions to have us questioning this whole thing. Or
the anthropic principle.
yeah,
The weak
exactly.
anthropic principle, which says that
Exactly.
the how you say, the response, the answer to the question why, which I find it, if I think about it, I find it counterintuitive, and then I have to think about it, because it is pretty much the response, the answer you give to the question, why is the universe like this? And the answer is the universe is like this because you can observe it, basically. Which if one thinks logically about it, says, wait, but this is a circular reasoning.
Exactly.
Well,
It's a loop.
that's how it is. So
It's a thinking loop, yeah. But so that first 3 minutes are the most important part. The good thing is we had photons. I think that's what I'm assuming. We had photons just after the Big Bang, just after the Big Bang. So light was there, photons was there, and things happened, and everything happened, and so universe started expanding. Electrons had to travel a little bit far away. So after some point, they started orbiting the protons, or for example the nucleons. We get hydrogen and helium, and everything cools. There's nothing literally happening till the first stars form, and that portion is we call dark ages, because there's literally no light, legit no light in the universe. So there's whole information gap there. And I don't think so anything gravitationally happened. Maybe it happened, maybe it didn't, I don't know. Maybe some events should have happened which might have caused fluctuations in the space time itself, that we might be able to track with Lisa, but I'm really not sure. But yeah, there's this huge information gap, and then the first stars form, and then we have the light. So if you have seen that CMB diagram, that blotchy thing, yeah. So
the cosmic microwave background radiation we're talking about.
exactly. So if you see, that's a temperature background. So it tells about the temperature in the terms of temperature. So you see some of the places have a higher temperature, some of the places have a lower temperature. So and the places where you have the higher temperatures are basically the potential wells where galaxies started forming. So you need dark matter simulations to say, because wherever the galaxies form, they form at the potential well created by the dark matter halo. So every galaxy is surrounded by a dark matter halo. So it's dark matter started getting spread in the universe heterogeneously, and matter started falling in their potential wells, and then we got the galaxies. So it went something like this. So we need very strong, very robust hydrodynamical simulations to remove all those things from the CMB background, and then we will get the pure light which we had from the first 3 minutes. So that's how you aim to find things out. So there are hypotheses. There should be a gravitational footprint, we say, which we aim to detect from Lisa, which is space-based LIGO, something like that. But yeah, it's going to be huge task to find that all those things. So if you know where to look at, you are then not bounded by light. You can actually get pretty much everything out of it. But I mean, if we can trace back how the first 3 minutes happened in a specific way, we might be able to find out what actually happened at the singularity, from where the universe came. So
that would be interesting to know. Yes, definitely.
But yeah, again, I think that regime is completely out of our reach.
Yeah, the thing is that reading, I do understand that physics there was not much, was very, very much different than what we can even comprehend. So even, let's say, mathematically, physically, let's say even physically constructing a mathematical framework that can hold in those very little moments, as you said, in the first 3 minutes, it's very tough to do. So yes, it's a great challenge, but I think it is the purpose of the theory of quantum gravity, which I believe it can be, not it can be, it, I would say, hopefully it can give us some valuable insights on what was going on in the either quantum theory or string theory, whatever it is. I don't care. I just would like to hear some answers.
What the hell happened there? Yeah, just me like the good thing, like, studying here, like at the Heidelberg is you have almost all the groups, like, working from the smallest to the largest things in the universe. And so you sometimes you get lectures from them, and sometimes, like, just random lectures. Sometimes if the professor is taking a class, he gives us those few bits of excitement, like, this happened like this happened like this, for example. And like, this is a pretty cool thing which I find about here. You can go, if you have a question, you can find someone who can answer that question. Like, it's a pretty cool thing here, to have that privilege. And like, there is this really cool professor, I guess I don't remember the first name. I'm really bad at remembering the names, but I just remember the last time. It's like Dr. Bartleman. He is like one of the group leads here, which work on cosmic structure formation, like how the cosmic structure came. So how the hydrodynamical simulations form from the dark matter itself and everything. And like they know like what happened. Like, I mean, they would be way better to answer this question. Like, are we really bounded by light, or how much information do we really know? Like, how, because there are cosmologists working on this day and night from ages, literally. All the departments at the Caltech, MIT, Harvard, they're proud. Like at Princeton, they're proud because they every day they go, they go there in their office, they sit, and they start deducing it from the very scratch, like why it's happening like this. So they already might know a lot more stuff. But we are in the era of internet, and we have a lot of people, like, sitting free in the home and, like, creating content. So finding the real answer, real information is really hard nowadays. So yeah, like,
yes, maybe hopefully we may meet again one day, talking about the answer we have been told that we have found out.
Do you remember this? This happens like this. Yeah.
hopefully it can happen.
Yeah.
But okay. So yes, I will greet you, Bhavesh, and I will thank you for the time you gave us. And I believe it was very exciting. You gave us a lot of theory and a lot of details, which I found very fascinating. So I thank you first for your time and for your availability. And of course, I do want to wish you good luck with your master studies, and with your experience at the Max Planck Institute, which is a prestigious institution at which to, let's say, how do you say, get rid, not get rid, I say let off a little bit of your of this passion and this geek interest.
No, thanks for having me. Like, it's been a long time I've been, like, talking out in the public, talking about the things I like. So it's been a really long time. For almost a year, I haven't done this. So it was really refreshing for me, like, to share my excitement with someone, like, just happens like this. Like, yeah.
that's the purpose. That's the purpose of this podcast.
Thank you for having me. Like,
yep. So I think we can wrap it up. So thanks to Bhavesh firstly, but thanks to whoever is listening. And so this was Math and Beyond, and we will see you. We are greeting you, and we will see you on the next episode.
Okay. Bye-bye.